Hello everyone. Welcome to the webinar on Intro to Apache Apex, the next generation Hadoop platform for ingestion and transformation. My name is Pramod Immaneni. I'm a PMC member of Apache Apex and senior architect at DataTorrent. Um, uh, just a quick couple of things. If you have any questions during the talk, feel free to type in your question in the in the question section in the webinar tool, and I'll try to answer them as soon as I can. So I would like to start with a brief introduction to Apex. So Apex started out as a started out in DataTorrent, the company I worked for. It was initially proprietary software. It was we started building it about 4 years back, and it was one of the first applications on Hadoop Yarn. So when Hadoop Yarn was released, other than the MapReduce application that it came bundled with, we were probably the first third-party application that was available on Hadoop Yarn. And then last year, we made our streaming platform or our engine open source, and we called the project Apex. We released it under the Apache Foundation, and this year we became a top-level project. Okay, with that, I'd like to start. So traditionally, with Hadoop, you were Hadoop's in Hadoop, when you're processing big data, you're dealing with files. So you're basically processing large files, and so your entire processing paradigm was around files. So if you look at MapReduce, most of your processing, you're taking some files, doing some computations, writing some intermediate files, and then the next stage of processing again picks up those intermediate files, does further processing, and creates the final outputs. But in the last few years, what has happened is the kinds of data that's now coming in is kind of shifting from like traditional file-based sources to more streaming sources. So you have an explosion of IoT devices, Internet of Things devices, whether it's consumer type devices like you know like thermostats or lights, or other kinds of home automation control devices, or even devices of the industrial internet and in manufacturing. Of course, you have other kinds of streaming sources like social media as well. And also what has happened is Kafka, which is has gained popularity. So Kafka is a message bus to consume streaming data. So that has also gained quite a lot of popularity. So now you could actually ingest data via Kafka from these streaming sources and do some complex processing or whatever custom processing you want to do. So what this means is that data is coming in, large amounts of data is coming in, and it's coming in continuously at a high rate, which means you need to be able to process the data at that speed, and basically you cannot take a lot of time to process the data. So which means that the processing has to shift to an in-memory type solution, which is doing very little file I/O. So that otherwise, you basically not be able to handle the velocity at which the data is coming in. And of course, to produce a meaningful application, you need to be able to do different types of operations like aggregations, or rule-based processing, or different kinds of processing. And a lot of these require that you keep memory as you're processing data. So that when you're processing a future data, the results depend on some computations you made based on the current data, right? And of course, the whatever platform you choose to do this processing should be able to support a variety of things, and so that you can write to a variety of output output stores, like whether it's traditional databases or NoSQL key value stores, or even into Hadoop files. So Apex was designed for to handle all these scenarios. And at the bottom of the slide, you see a sample flow, sample application flow, where you may have a bunch of web servers that have some logs collected. So it could be the access logs, of different clients accessing this web server, and you want to do some processing of these logs. So these logs can be fed to Kafka via a syslog server, and then as the logs are coming in, you could do some, you basically parse it, and you do some filtering, and you may then perform some kind of dimensional aggregations, such as you want to find out which client IP addresses are making the most amount of requests, or what combination of user agent and or basically what combination of client IP and a particular web page is having the most hits. So and then you may want to write those those insights that you computed back out to Kafka or any other store for further processing or further analysis. So this is just a sample kind of application, but with Apex you can build any type of general purpose application. So like I mentioned, Apex is a in-memory distributed stream processing application that runs on Hadoop. So what does it mean by let's start with what does it mean by distributed, right? So what you do is, first you take your application logic, whatever you want to build, and you break it into smaller logical components and of logic, and these are called operators. So this is a job that you as an application developer would do, right? So let's say I want to build an application where I want to read some data, read some streaming data, and I want to do some cleanup of the data, and then I want to parse the data, do some cleanup, and store it into, like, let's say, a database. Then I would probably create 4 operators. The first operator I would read from the source, whether it's Kafka, whether it's files, whether it is anything else, doesn't matter. And in the second operator, I would actually parse the data. In the third operator, I would clean up or filter the data. And in the last operator, I will write it to the database, right? So basically, I would create those 4 operators, and then I would basically connect them up, and then I'll ask Apex to run it. So what happens is these operators would then run across your Hadoop cluster. So they may end up as running as different processes on different machines. Okay, and the data between these different operators flows directly from operator to operator over the network. So there is no touching of files. It doesn't get stored into something like HDFS and read back in. So so that doesn't happen. It directly goes over the network. So that actually ensures that you're able to process the data. The data is basically getting processed quickly throughout the application, and eventually coming out. And you're able to handle high velocity streams. And each of these operators can basically contain any custom logic you want. So you basically write your logic in Java, and it can basically be can express any custom logic you want. And the Apex API is very simple. With the API, what you can do is you can send data to the next operator for processing, or when you receive data from the previous operator, the API gives the data to you immediately. And it's a true event processing model. So as soon as you emit a piece of data or send a piece of data to the next operator, the platform, Apex platform, will try to get it to the next operator as soon as possible. So it doesn't artificially batch the data or anything like that, right? So you can get end-to-end latencies in the order of milliseconds or even sub-milliseconds, even though your application is pipelined and actually running in multiple processes. Next, it is highly scalable. So what it means is each of your operators can actually run in multiple processes and parallelly handle a lot of data. So you could, for example, be bringing in data from, let's say, have an input operator that's actually reading from some let's say a folder, right? And you're reading from some files. You can actually have multiple instances of that operator, and each of them is reading from a different file. So you're parallelly reading multiple files and bringing in data. And the next stage of parsing could also happen in parallel in multiple processes, and each of them are parsing different subsets of the data. So that's how you get scalability and ability to process big data, streaming big data. And something we also support, which is fairly unique, is dynamic scaling. So each of these operators the number of instances or number of instances of each of these operator processes can actually increase or decrease based on the load. And the next important feature of the platform is fault tolerance. So what happens if any of your nodes go down, or you have any outages in your Hadoop cluster, and that basically takes down some of these operators. The Apex engine is smart enough to figure out what pieces of the application have gone down, and it will quickly recover them without any data loss. Okay, and it will still ensure that all your calculations and whatever logic you're performing still leads to correct results. Okay, and and with Apex you can also achieve what's called end-to-end exactly once. So essentially this is let's say if you're writing your output to some output store, and you basically want to make sure that even in case of failures, your no data is lost in the output, or no data is duplicated in the output. So all the calculations happen correctly, and the results are stored correctly in the output, even in the face of failures. And on top of the Apex platform, DataTorrent provides some tools that make it easier for you to basically run these applications, or from an operational point of view, monitor these applications as they're running. And we'll look at those in the future slides. So there's a question: how do you achieve the exactly once guarantees? Sure, it's a good question. I have a couple of slides towards the latter part of the presentation that take up two particular examples and show you that. And it'll become a little more clearer at the time. And I have a complete, I have a slide dedicated for that. Okay. All right. So an overview of the Hadoop or Apex stack. So all Apex needs is Hadoop. Doesn't require any other piece of software. So so it's Hadoop 2.0 or above, which is Yarn and HDFS, right? So Hadoop 2.0 above are basically composed of two main components, Yarn and HDFS. HDFS is for the storage, and Yarn basically handles the resource allocation and scheduling part part of the distributed platform. So so Apex runs on top of Hadoop, and you could be running on a physical cluster. You could be running on a VM-based cluster, or you could even be running on cloud like AWS or Azure or any of those platforms. Now, on top of the streaming runtime engine would be your applications that are running. So when your applications are running on the Hadoop cluster, so they will run along with the Apex streaming runtime. Now, like I mentioned, your application would be composed of operators, right? So many times, there are in an application there are some commonly used operators, right? So, for example, an operator to read from Kafka, or an operator to write to a database, or an operator to do some JSON parsing. So this is common functionality that won't change much from application to application, right? Or from from one user to the other. So we actually also provide a big library of operators in the Apex project that are ready to use, so that you can incorporate them into your application and get the ground running pretty quickly, and then basically just build out your specific operators that you need for your application, and you're not basically having to build all the general purpose ones, right? So that's the Malhar library. Now, on top of this, DataTorrent provides a few different tools. So the first is the management console. So the management console is actually a pretty versatile tool that actually shows you the complete detailed information of our application as it's running in the cluster. So let's say your application has 15 operators, and each operator actually has multiple processes, or it has scaled into multiple, we call them partitions. So it could actually be, you could even run into hundreds of these operator instances, and the management console actually will show you all of them in a neat way, so that you can actually see where they are running, how much resources they are utilizing, how are they performing. You can even look at the logs. You can even record data as it's flowing through each of these individual components, and so it gives you a full operational view. And if there have been some failure recoveries or any other major events, you can all see them there as well. Now, the second component is a visualization dashboard. So if you are actually in your application, you want to build some output visualization where you want to in real time see the output, you can do that as well. So we provide some highly high performing widget library that can basically receive streaming data and show you the output. Like we have different kinds of charts, or we have even with geo widgets and chloroplates and so on. And we also have a graphical studio where you can design your applications by connecting these operators and configuring them quickly. So if you already have the operators built in Java, you can use it in this tool, and you can quickly compose your application pipelines. Okay. So what do I mean by native Hadoop integration is actually this picture illustrates that. So let's say you have a Hadoop cluster, typically has a resource manager, and if you're running in HA, you may have a secondary one as well. And then you have the node managers, which are actually running on all the worker nodes where the applications are going to run. So on these node managers is where the application would be deployed and running. So in this case, this picture is showing a sample application with 6 operators numbered 1 to 6, and these 6 are actually deployed across the different nodes of your cluster. So each of these boxes are actually is running as a independent process, is independent Java process. So you can see that 1 and 2 are actually on different machines. 3 and 5 are actually running as different process but on the same machine, and 4 and 6 are actually running as threads inside the same process. So the operators can run in all these various fashions. They could be just independent processes or even threads. And you can actually control this, and there are different advantages for running it in these different ways. So for example, if 4 and 6 are running inside the same process, then the data that's being transmitted between them doesn't have to get serialized. It goes through an in-memory queue. Now, if 3 and 5 are in the same machine, the data doesn't have to go over your network hardware or your network switches, right? It basically just goes through the local loop back, so it doesn't affect the network bandwidth. And 1 and 2, which are just running on different machines, data goes over the network, serialized and goes over the network and gets deserialized on the other end. But now, since they're running as different processes, they can, they basically won't affect. So they're just using independent CPUs, and they basically can utilize the full processing power of those of whatever those machines can offer without any affecting each other. And then you see some MapReduce blocks here. We don't use MapReduce or anything like that. This is just to show you that you don't have to dedicate a cluster for Apex. You can run it alongside any other Hadoop applications you want, and Apex applications can be running while your other applications are running, like other MapReduce applications are running, and they won't interfere with those. So they can just coexist easily. And then on the top you see some boxes. So Apex CLI is a command line tool that you use to launch applications or even get information from a running application. So you just need to install that on one machine. It could be a machine on your Hadoop cluster, or it could be an edge node that has access to the Hadoop cluster. And if you're using the DataTorrent Enterprise Edition offering, then there are UI tools to do the same job that the CLI provides, right? And then the UI tool has two components as well. So the UI is called console, and in the backing it, there is a service called gateway. Again, in that case also you would just install them on one node. Okay. So there's a question, how data is persisted during processing. For instance, what happens if node 4 and 6 die? So data doesn't get persisted. Interesting, good question. So if 4 and 6 die, then the data is available in 3. Let's say 3 is the upstream operator for 4. It's available in a buffer in 3, and when 4 is restarted from a checkpoint, it will basically recover the data from 3. And we'll look at this in a little more detail so it becomes clear. So let's look at the application development model. So in this slide, we'll introduce a few terms. And then we'll use that in the rest of the presentation. So like I mentioned, you basically take your application and break them up into operators. So this application is showing you 6 operators. So the first operator that is special in the sense that it has no other operator before it, so it has to bring data from somewhere externally. So we call those input operators. Again, your input could be anything. It could be bringing data from a Kafka queue. It could be from some other JMS queue. It could be from files. It could be reading from databases. The platform does not care where you're getting data from. It's just another operator. And we have a whole bunch of those in our library as well, right, that you can ready to use. And then this operator, as soon as it gets a piece of data, it will just send it out for the next operator to consume. So each piece of data is called a tuple, and you could be sending anything there. You could be sending simple things like strings or integers, or any other primitives, or you can even send any complex object. You can send POJOs or any other deeply nested object, right? That's fine. It gets serialized, and on the other side it will get deserialized and appear for the other operator in the same form. So this stream of this data is we call it a stream. As the data flow, we just call it a stream. So the next operator, for example, so the first operator maybe is bringing data, reading data from a file line by line, sending the line. The next operator could be parsing that, right? So it could be a parser that's parsing it, or doing some filtering and sending out to the next operator, which is doing some enrichment. And it's actually the second operator actually sent it output to two different operators, which is also possible. And let's say they both are doing some enrichments and their results are getting merged by the fifth operator in the stream, and then it's sending the output to some output operator, which could be again writing the output somewhere else. Could be writing to a database, NoSQL store, or it could also be writing to HDFS, right? So this entire and what you do is you basically create these operators, and then with our API you even connect them up. So with the Apex API you basically connect these operators together, and this whole thing together is called a DAG. This is a standard industry term, a direct acyclic graph. Okay, and again, as I mentioned, your operators can be any logic you like. And for each operator, you actually see a multi-dimensional view of other boxes in different planes. This is to just show that you can actually, the same logic of the operator could actually be running in multiple processes. We call them partitions, so that each of them are actually processing a subset of the incoming data, and overall they could be together, they could be processing a lot more data than just running the operator in a single instance. So there's a question: can Apex also be used without a Hadoop cluster? Today, it needs to run on Hadoop, but we have in our roadmap an initiative to support Mesos in the future as well. But I think you may also have success probably running it under Myriad, as a bridge between Yarn and Mesos. There's a question: would the node manager be distributed among the nodes even if it's used with Hadoop, which has its NM on one and only one node? So we don't implement a node manager of our own or anything like that. So we are using Hadoop scheduling, Yarn scheduling. So if you only have one node in your Hadoop cluster, that's fine. All these operators would just run on that node. Okay, so so that's kind of just depends on how many nodes you have in your cluster that are running node managers. We basically run on those number of nodes. So I basically want to dive in a little bit into the data flow. So in this picture, you actually is actually showing a data flow, and in between those colored circles, there is actually white circles which are slightly difficult to see. But those white circles are, let's say, represent data, and so the data is flowing through. It's coming into an operator. Operator is doing something with the data and sending some other data out, right? And this entire thing is kind of like flowing through your application DAG. Now, at the beginning, what we do is we insert some special pieces of data at different points in this data stream. So the first pieces of data that we insert are actually called window markers. So these are inserted every 500 milliseconds. So it's really lightweight, and it's a really small percentage of your actual data flow. So why do we do that, right? So this helps us to do some periodic bookkeeping, right? So at the beginning and end of the window, we can do some things. So for example, we want to we basically want to calculate stats. What happens at every 500 milliseconds. We want to know, okay, how your operator is performing. How much data it's processing, what's its latency, and so on. We also allow you to change some behavior of these operators at these window boundaries. This could be things like you can change certain properties. Let's say you are uh, 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 let's say you have an alert threshold, right? And then you want to change that alert, your data coming in, and if the data is less than the alert threshold, you don't do anything. But if it crosses this alert threshold, you want to send an email or something like that, right? Let's say you want to change the threshold. If you feel the threshold is too low, you want to change it, and you don't want to take down this application. So what you can do is, while the application is running, you can say, okay, I want to change the threshold. Now what will happen is, in the next window boundary, that change will be delivered to the operator, and the operator can now use the new threshold. So by doing that in this controlled fashion at these boundaries, we can do this in an we can do this in an idempotent way, in the sense that, if there is a failure, and there's a recovery or a fault tolerant recovery, we know exactly where this thing changed. We can affect the change exactly the same way the next time as well. And in case of dynamic scaling, when the partitions of an operator increase or decrease, those also happen at these boundaries. Now, there is a yellow circle that you can see in this picture. So this is called this is used for checkpointing. So this also happens at a window boundary, but not every window boundary. So this happens every 60 windows by default, which is every 30 seconds. So when an operator receives this checkpoint tuple, or this checkpoint metadata, its state is checkpointed. So what does it mean, right? So state is so your operator can actually have memory. So it can keep some whatever it wants in its memory for and use it for future processing, right? So let's say you're doing aggregates and you're counting something. So as data is coming in, you're updating your counts, right? And these counts will remain in your memory. And let's say there is a failure and the operator goes down and we recover, the counts don't go back to zero. So the counts will be preserved and will be available on a restart. So how is that possible? Because periodically we are saving whatever your operator has in your memory, we're automatically saving it to disk. So in this case, by default, we save it to HDFS, right? So again, we're not saving the data, we are saving the state or the memory of your operator. And you don't have to do anything special while you're writing your operator. Any variable, any non-transient variable that you have in your operator would basically get checkpointed. So this checkpointing, because the checkpointing is not is controlled through the data itself, all these operators in the DAG can checkpoint at the same point, and it can happen in distributed fashion, because as this checkpoint tuple is flowing through the DAG, each operator will basically checkpoint its state when that piece of data is received, right? So they all checkpoint at the same point in the data flow, and it can all happen distributedly without any bottleneck. And another important thing I wanted to mention is this windowing does not add to any latencies, because windowing doesn't mean the data is getting batched. The data is still arrives to you immediately as soon as the previous operator has sent it. And these are like just boundary markers. Okay. So sometimes you may need to do so in the previous slide, these window boundaries are actually processing time window boundaries, right? Because this is at the data when you're processing. That's when these boundaries are being inserted, and your operator also can do something at these window boundaries. So the API gives you a callback to kind of if you want to do some periodic processing, like you want to periodically emit the counts that you have so far calculated, you can do that as well, because so these window boundaries, the engine notifies you as well. So, but let's say you want to do something that's based on the event time of, let's say your data itself has a timestamp on when the data was generated, and you want to do some processing based on that timestamp and not on the current timestamp when the data is actually getting processed, right? So you could do that as well. We support operators to do that. One such operator is called dimension computation. And with this operator, you can do, I think what's one of the industry term is called cubing, right? So let's say your data has many different keys and timestamps. So and then you want to find out you want to basically do compute aggregates on different values of those keys for different time buckets, right? So in this case, let's say you have a data has a key and called k, which can have different values, and it has a timestamp, right? So what you want to do is compute how many times k equal to a was received from 4 to 5 p.m. yesterday, or 4 to 5 p.m. In the last month. Sorry, how many times k equal to a was received in the last month, or how many times it was received in last day from in a particular 1 hour or a per minute or a per day time bucket. So this operator lets you do that. So here, let's say in the first window we received just one piece of data, k equal to a, time equal to 4. Then basically it updates its aggregation map. So overall you just received one piece of data. If you want to say how many pieces of data you received in the time bucket from 4 to 5, that's also 1, and a combination of keys equal to a and time equal to 4 is 1. Let's say in the next window you received 3 more pieces of data, and now if you want to look at the aggregate map, you can see that for time bucket 4 to 5, now there is actually overall 2 pieces of data. The one that was received in the previous window, and in this window also you had one that you received with the timestamp of 4:30. So from 4 to 5, now you actually have 2. And then from 5 to 6, you have 2 as well, which is keys equal to b, right? And overall, then if you want to do the combination of key equal to a and time bucket 4 to 5, that's 2 events as well. And for key equal to b, time bucket 5 to 6, that's 2 events as well. And then if you now in the third window, if you receive key equal to a, time equal to 5, then these aggregates will get updated accordingly. So as you're receiving these data, these different combinations of these keys and time buckets can be calculated and used. Okay. Next, let's get into a little bit into scalability. So let's say in this on the left side you see a sample application with 3 operators, 0, 1, and 2. 0 could be an input operator fetching data from somewhere. 1, let's say, is doing some parsing, and let's say 2 is doing some output. Now 0 is probably pretty light on the CPU because all it's doing is fetching data, but 1 is actually doing more work. It's actually doing parsing, and it's slightly heavier on the CPU. So now to process all the data that 0 is producing, you may actually need multiple partitions or multiple instances of 1 to handle the speed at which 0 can bring data, right? So in this case, you can choose how many partitions you want for 1. So in this case, there are 3 partitions that are running. So basically, the logic of one parsing logic is actually running in 3 different processes, and each process is receiving subset of the data that's being sent out from 0. And now that the data is being separated into 3 streams, right? The results of the stage 1 would need to be unified before it gets to the next stage, right? So the unifier could be as simple as merging the streams. So if it's something like parsing, each piece of data is independent and the outputs can just be merged. But if you're doing some sort of mathematical computation or some other sort of analytics, the merge may not be that simple. It may actually need to involve other calculations, right? So for example, if one is computing sum, then the then each of these partitions now have partial sums because they received subsets of the data, right? So the individual sums would have to be added again to create the final sum, right? So the unifier at that time you basically can specify logic for the unifier, and that will also run as a separate operator. Now on the right side, you see a more realistic case where you have multiple stages and each stage needs to be partitioned. So in this case, operators 1 and 2 are both partitioned, and you can have different number of partitions for each stage. And in this case, what we do by default is we insert separate unifiers for each of the downstream partitions, so that there is no single bottleneck of all the results of the first partition coming in and then again splitting. And then some more advanced partitioning. So there's a question: how does Apex compute parallelism degree? Is it a setting set by the developer or can be automatically computed? Actually, the answer is both. You can do a fixed number of partitions for each. You can basically set the number of partitions for each stage, and when you before your application starts, and then each of those stages will start with those number of partitions. Or you can do a dynamic partitioning mechanism where you basically specify how and when to scale, and we actually have an API to do that, and we provide some default scalars that you can use, and I'll cover that in the very next slide as well. So so in this case, so on the left you see what's called parallel partitioning. So let's say you want to perform a series of operations on a piece of data, and there is really no need to shuffle the data across stages. You can use parallel partitioning. So for example, let's say you get a line, you want to parse it, then you want to filter it, like drop it if if the certain one of the fields has some value or something like that, and then you want to do some enrichment, add some more fields to the parsed data. So essentially, you're performing a bunch of operations, series of operations on the same data. So in that case, you can connect these three stages in a parallel partition. So then each stage will have the same number of partitions, and the data doesn't get shuffled. So for example, 1A's data directly goes to 2A, right? So it's much faster than if data was getting shuffled across stages. And on the right side, you see what's called cascade unification. So if you have a lot of partitions, so essentially you're computing, you have a lot of data coming in, and you're actually handling it with multiple different partitions, and now you need to unify the results, bring it down into one output, but you have so many partitions that it's not possible to bring it into one operator, because that might create a huge bottleneck. So what you can do is now you can unify in stages, right? So it's very easy. All you do is you specify number of partitions a unifier can handle. That's it, right? So in this picture, let's say for an example, let's say you have 4 partitions, but a unifier can only handle 2 of them. So basically you can just say that that's what you say, a unifier can handle 2, and the platform will insert multiple stages of unifiers. So it will first insert 2 unifiers, each of them consuming from 2 upstream partitions, and another unifier that's getting the result of the first stage of unifiers. So these 3 unifiers with these different stages are automatically created and inserted. All you have to specify is that a unifier could only handle 2, right? If you don't do that, then essentially you'll put 1 unifier for all the 4. I mean, this is just an illustrative example. For 2 partitions or 4 partitions, the unifier should be able to handle it in typical circumstances. But let's say you have hundreds of partitions, right? Then this becomes more useful. Okay. So next is dynamic partitioning, which is again fairly unique to what Apex in this space. This is what Apex provides. So this is actually scaling your operators while the application is running. So let's say your application starts out with 2 partitions of stage 1 and stage 2, and you have more data coming in. And let's say stage 1 is able to handle that. It's lightweight. It has enough reserve CPU that it's able to do that. But in stage 2, you're doing more complex processing, and if you don't increase the partitions, you might slow down the processing, right? You might not be able to handle the incoming data rate. So in which case now stage 2 can actually dynamically scale from 2 to 4, and let's say that's now producing more data for stage 3, and stage 3 can also then scale from 1 to 2. So we provide a default. So in our case, in what we have done is this: we realized that this scaling um, is basically is something that the users would like to have a lot of control on, and because each case is different, so we provide some default scalars, but we also have an API that the users can use to build their own scalars, right? So we provide out of the box, we provide throughput based and latency based scalars. So what you can say is what is your throughput maximum that a partition can handle. So you can say, okay, my partition can handle 20,000 pieces of data per second. Now, when the incoming data rate increases more than that, then the engine will scale and create more partitions for you. And then till the incoming data per partition goes down to less than 20,000, right? So that's configurable. But so that's how it will create more partitions. And then when the data flow decreases, then it will combine the partitions back and will reduce the number of partitions back to the original. Similarly, we have a latency-based partitioner where you specify it based on a latency limit, and if the latency limit starts increasing, and latency of the operator starts increasing, then it will create more partitions to handle the load. Now, you may want to do some your own custom scaling. Maybe you expect data flow to be high at 10 a.m. and you want at 9:30 a.m. you want to increase the number of partitions and bring it down after 3 p.m. You can do that because we have an API for you to write your own scalars, and you can write that and you can assign it to the operators. And sometimes while writing the operator itself, you can provide a default scalar. So one example is our Kafka input operator that reads from Kafka. What it does is it has a custom scalar. It goes and looks into on the Kafka side, and on the Kafka, in Kafka, what you can do is for a topic you can actually have multiple brokers or multiple partitions on the Kafka side itself. So it figures out the number of partitions on the Kafka side and creates an equivalent number of partitions on the Apex side, so that each of them can parallelly read from the different Kafka partitions, right? So it can parallelly bring in data at the maximum speed possible, because each of those are independently running and bringing the data from the different Kafka partitions parallelly. So there's a question: how operators are distributed over yarn containers? If we have more operators than nodes, do we create several containers per node? Or do we run several operators in each container? So it's a good question. So by default, when you don't specify any what's called we call locality, then we try to put each operator in its own process. And if there are more operators than nodes, and of course some of these some nodes may have multiple processes running, but you also have the ability to put operators, specify that certain operators should be in the same process. Then they will run as threads within the same process, right? So you have control over that. So if you remember the parallel partitioning picture before, you can, for example, put 1, 2, and 3 into the same container because they're operating their series of operations on the same data. So they could, so 1A, 2A, and 3A will run in the same process. 1B, 2B, 3B would run in the same process as separate threads, and it would be more optimal. Okay. Right. So so the next important piece is fault tolerance. So just like scaling is important to Apex, fault tolerance is equally important. So we basically the way the platform was designed for long-running applications, right? So basically your applications are running and continuously processing data, and you may shut it down after a month, a year, or maybe never, right? So that's our goal, so that you don't have to take down your application. So which means that we need to be able to handle failures in your cluster, because you may some nodes may go down at some point of time, or they may be taken down for maintenance. So we can't expect the users to figure out what to do in those scenarios with the application. So what happens is the so along with your application, along with your operators, there is some engine, streaming Apex engine is running, right? So it will detect when the nodes have gone down, or when the operators have gone down, and it will smartly restore those operators from the checkpoint. So what I mean by smartly is, let's say you have 5 operators and operator 3 went down, right? Operators 1 and 2 will continue to run as they are running without any problem. The platform will recognize that 3 has gone down. It will restore 3 from the checkpoint, and then it will rewind 4 and 5 also back to the checkpoints, because they are receiving data from 3. And so 3 has gone back a little bit and is going to reprocess a little bit of data. So to have basically make sure that the results are consistent, it will rewind 4 and 5 also back to the checkpoint, and basically they are then just reprocessing that small amount of data from the checkpoint. And so for this all to work, essentially each operator state is being checkpointed, right? Which we saw earlier. Each operator is being checkpointed by default every 30 seconds. So worst case, when an operator goes down, it's going to be restarted from an image that's 30 seconds old. But when it gets restarted from the checkpoint, it will basically receive the very next piece of data from that checkpoint, right? So it's kind of like it's going back and kind of replaying. So there's a question: does Apex use zookeeper underneath? No, Apex doesn't use zookeeper underneath. We have our own checkpointing mechanism. So now, how do we recognize that operators or nodes have gone down? First, we have our own internal heartbeat mechanism. So the individual operators, they run in what are called streaming containers, and these streaming containers are pinging our application master, which is running alongside your application. And if these heartbeats are not received for a certain period of time, then the application master knows that the operators have gone down and initiate failure recovery. And sometimes Yarn would also notify us. Now, there was a question earlier on, what happens to the data, right? So let's say you had operators 1, 2, 3, 4, and 5. 3 went down, 3 came back up from the checkpoint, right? So let's say it was at window number 70 when it died, and checkpoint happened at window 60. It will restart. We'll restart it from 60, and then it'll get the immediate data from Windows 61, right? So where is the data for Windows 61? Because the operator just died and came back, right? The data for the Windows 61 is actually in the upstream operator in a buffer. So operator number 2, so each operator has a buffer where the data is also stored for the downstream operators, right? In case of failure recovery. So these buffers don't grow independently, grow indefinitely, right? So once all the operators have checkpointed, right, in the DAG have checkpointed beyond a point, the old data in these buffers are automatically purged. So all these buffers are kind of moving forward as well. So if let's say all operators have gone beyond window 120 and they all checkpointed beyond 120, we don't need data before 120 anymore. So that's kind of discarded. So that's how that works. And this buffer also allows everything to be asynchronous. So the operators can, each operator can basically send data and not get blocked till the next operator gets the data, right? And also and essentially this helps us in doing incremental failure recovery, right? So if operator 3 goes down, we don't have to restart 1 and 2. 1 and 2 don't even know that 3 has gone down if they're continuing to progress wherever they were already processing. And when 3 comes back up from failure recovery, it will start from the checkpoint data. I mean, from the checkpoints point in window, and it will start pulling out the data and quickly catch up. Good question. There's a question: what happens if the first operator dies? So in that case, the first operator would need to replay the data from somewhere, right? So there are different scenarios here. So if the first operator is something like a Kafka operator, then the Kafka operator maintains its offset in its state. So when the operator is restarted, the platform will automatically recover the offset for you and give you the offset. So then the Kafka operator is relying on Kafka and is basically replaying data from the offset, and Kafka persists the data, right? So, or if your input data is a file operator, it could again use an offset to replay the old data. Or if it's from a database, it'll have to keep some track of, some timestamp or something where to read data from. But what if your input source doesn't have memory, right? And your operator is just reading data from it, and then the input source doesn't have a way to replay the data for you, preserve the old data for you. In that case, then the operator would have to do the work to save the data itself, so that in case it needs it for failure recovery. And we provide tools for that. We call it Window Data Manager. It's a utility available in our library. If your input source doesn't have memory, and your input operator has to handle it itself. Okay. Now, also what happens is the Apex application master that is running alongside your operators, it also checkpoints its state. So just in case, because it's running in a container as well, and if that container goes down for any reason, then we are able to recover the state of the application as well. So it also preserves its state. And there is an interesting corollary to all this is you can actually completely shut down the application as well, and restart the application from where the previous instance stopped, right? So you can actually shut down the application and then restart it, and pointing it to the checkpoints of the previous application, and it will continue from where it left off, right? So that's the other side benefit of basically being able to do fault tolerance. If one operator fails, or multiple operator fails, or even if the entire application fails, it can recover. So the buffer server, which I alluded to in the previous slide, basically is critical for incremental recovery. So here, let's say you have two operators, operator 1 and 2. So operator 1 is writing data, basically sending data to operator 2. It's asynchronous for operator 1. As soon as it sends the data, the control returns, and operator 1 can continue processing. The data is basically put in this buffer and also sent to operator 2, and it's available in the buffer till operator 2 will no longer need it. So till operator 2 has checkpointed, not just operator 2, all the operators beyond operator 2 have also checkpointed beyond a certain window. That data will still be available in the buffer in case any of them fail and they need the data again. So the buffer also allows us to basically provide overall higher utilization. So for example, let's say there is a sudden slowdown in node 2 for some reason. Let's say there's suddenly a big disk usage by some other application running on node 2, and operator 2 doesn't get enough CPU and gets slowed down. That doesn't slow down operator 1, because this buffer acts like a valve, right? So like a queue. So operator 1 could be still working at its pace and filling the queue, and then operator 2, when it gets back its CPU cycles, now pulls the data from the buffer, and then it could catch up, right? And it doesn't, and in the end, it never slowed down operator 1 because of that. So let's look quickly at end-to-end exactly once. The recovery of the checkpoint recovery in case of failure, what I described is called at least once. The reason it's called at least once is what has happened is your operator basically was failed, so it basically got restarted from a checkpoint, and it started processing the data from the checkpoint again, right? So there was it restarted from an earlier point in time, and it reprocessed a small amount of data, right? So since it reprocessed a small amount of data, it's called at least once because it had processed the data before that's the small amount of data before it went down as well, right? Some people actually call it exactly once because it's kind of like rewinding, but actually it's not exactly once, it's at least once. So what does exactly end-to-end exactly once means? And so end-to-end exactly once means that let's say you are eventually writing the data to an output store, right? Now, when you're rewinding and reprocessing, you're still producing the same results, correct results. So for some people that might be okay, but let's say you're writing the data, so by rewinding and reprocessing, you're not losing any data, right? So there's no loss of data, so that's good. But let's say you're writing to an output store, you might be duplicating data in that output, right? Because you have written some data before failure, and because you're reprocessing that data again, that small amount of data you might be writing to the store again and creating duplicates. So end-to-end exactly once means you don't write any duplicates either when there's a failure, recovery, and reprocessing. So for that to happen, the platform alone cannot do it. So the platform along with the operator together can do it. So along with the cooperation of this external store, right? So so what happens is our operators, our output operators, if you look at them, they implement some handling to some special logic to basically ensure that we are end-to-end exactly once, right? So both are needed. So without the platform's state recovery, the operator cannot do it, and then the operator also, based on the external store it's writing to, has some logic to basically ensure that data is only written exactly once, even in case of failure, right? So let's look at some examples, right? So let's say you have an operator that's writing to an output file, okay? So let's say data is coming in to this operator and it's writing to this file, and periodically the state of this operator is being checkpointed at the checkpoint window boundaries. So the state actually for this operator is the file offset. So what it's doing is it's basically keeping the file offset in its memory, so that is being saved periodically. Just the offset is being saved as part of the checkpoint. So let's say there's a checkpoint that happened earlier and another checkpoint happened. So you have data that's some more data came in, and basically a window ended, a checkpoint happened, and now you wrote some more data to the file, and now let's say the operator failed, right? So now the file is going to contain all the data from the beginning to where the X is, right? But when the operator restarts from the checkpoint, its offset will be only where the arrow ends, right? So what the operator will do, the very first thing as soon as it starts, is it will truncate the file back to the checkpoint offset, right? And then because it's now reprocessing the data from the checkpoint again, it will start writing the data again, right? So okay, and essentially there won't be any duplicate, because it truncated the file and removed that extra data before it reprocessed. Okay, so that's how the file operator ensures a file operator works with the platform to ensure end-to-end exactly once. So the platform provided it the feature of giving it back the offset on recovery, and file offset did the file operator did the truncation, right? So both of them together work to get the exactly once. So let's take a look at the database operator and how it would work. So the database operator, what it does is it basically uses another meta table in your database. So let's say this operator is writing to a table, and it's writing some data to a table. It also requires another meta table, and in this meta table there's only, like, let's say one piece of data it stores, just one row, and in this row it stores the last processed window ID. So what it does is it writes data in every window in a single transaction, and along with this transaction it also writes the window ID, and at the end of the window it commits the transaction. So let's say the last fully processed window was wn. So then this meta table will contain wn along with your normal data in your normal data table. Now let's say the operator fails, right? Let's say that the node went down and that operator uh, went down because of that. So the extra data after window n, that transaction never got committed, right? So that data would never be even appear in your data table. But when the operator restarts, it will restart from the checkpoint, right? And it will receive all the data till window n again. But when the operator restarts, because it'll read the meta table and read the value wn back, and it will ignore all the windows till wn, so it won't write that again, right? Because it knows that it's already written that before, because that was in this meta table. And when it gets new data, it'll start writing again. And when window n+1 finishes, this meta table will now have window n+1. So so you'll actually see so different operators in our output operators in our library, basically doing these using different strategies to basically ensure that data is end-to-end exactly once, written in end-to-end exactly once. There's a question: does each tuple have a unique ID generated by Apex? No. So tuple is whatever data you send. There is no unique ID. It's just that there are window boundaries within which the data is, right? So at the beginning of the window, your operator gets a callback of the window ID, and then you get data, and then at the end of the window you get another callback. So you know that you could theoretically know which window data belongs to. But you can have if you want to add an ID to your piece of data, that's fine, and you can use it, because for us you can basically send any Java object. So what we have done is, so you saw the engine, you saw the operators. Now we also have some applications for folks to use if that application would solve their problem. So one such application is what we call Ingestion solution. This is currently in beta. This is being offered by DataTorrent. So in this, we have a whole bunch of operators that we have put together, and they are available in the DataTorrent Design Studio, where you can connect these operators up and create different kinds of ingestion pipelines. And the application also comes with a couple of pipelines. Let's say you wanted to read data from Kafka, parse it, do some deduping, do some transformation, store to HDFS. There's a pre-built application for that. Or if you wanted to sync between two clusters, HDFS clusters, or from sync from S3 to HDFS, that's available as well. Or you can actually create your own pipeline by using different combinations of these different operators that are available. So a bunch of input-output connectors and a bunch of processing connectors. And if you're interested, please send an email to info@datatorrent.com. So essentially, you'll see a designer like this, and you can drag and drop these operators and connect them up and create your solution, your ingestion solution. But let's say you're building your own application, from code. How would it look like? So we have two different APIs to construct your application. So first one is our low-level API, or a compositional API. So here you instantiate the different operators and you connect them up. So this is a simple word count example where data is being read line by line from some file. It's being parsed. Then so the first operator is reading a line from a file, sending it to the next operator, and it keeps on doing that. The next operator is breaking that line into words. The third one is counting how many times each word occurred, and every window it's emitting the counts to a console operator, which is just printing to a log file. So here you can see you just need to implement the streaming application interface, and there's just one method to implement, where you're given an empty DAG. The method receives an empty DAG as the parameter. It needs to fill up the DAG. So the first 4 lines are creating the 4 operators: line reader, parser, counter, console. Then then we are connecting them up. So the output of the line reader, so you connect them up with streams. So that's the add stream method. So you're connecting the output of line reader to the input of parser, output of parser to the input of counter, and output of counter to the input of console, right? So that will end up creating your DAG. So here it's assuming that these operators are already available, or basically they're written by you, right? That doesn't show the actual operators themselves. That will come to in the next slide. We also have a new API. This is more easier to use. We call it a high-level API. It's declarative. Here you specify what functionality you want to do on the data itself. So this is like some of the high-level API you may have seen with other engines as well. So here we're doing the same thing in a different way. So we are specifying that, okay, we want to read files from a folder, then apply a function on each piece of data. We're going to split the line based on word boundaries. Then we're going to count by the key, which is the words, and then we're going to print it. We're also adding windowing function, the event time windowing functionality directly to this high-level API. So you don't have to do any special operators for that. So in this case, we are saying that every 1 second output the counts, right? So you're saying keep accumulating the counts every so that cumulatively, and every 1 second output the current count. So this syntax it might look a little daunting, but actually this is a windowing syntax that Apache Beam, the windowing semantics that Apache Beam is also that they have popularized. It's being widely adopted as well. So this is the same windowing semantics. Okay. The question: how do you position Apex with Storm? So we are much more high performant than Storm. So with Storm, what happens is your data needs to be acknowledged on a tuple by tuple basis, and that essentially leads to lower throughput. With us, we don't need that, and we can still achieve fault tolerance without any loss of data. And then second is state management. State is automatically managed for you. So data, you don't have to do anything special for state. Your operator can just have anything it wants in its memory, and it will be saved and recovered for you as well. And other things like dynamic partitioning and other features that we have. So here, this picture is actually showing you, let's say you're building your own operators. How would it look like? So let's look at a simpler operator first, the parser. So what the parser is doing, and if you remember the previous picture, is it's getting lines and then it's breaking them into words and sending them, right? So to receive data, the operator defines what's called an input port, and it specifies a port, in this case a type, in this case a string. So as soon as a string arrives from the previous operator, the process method is called. So this callback method is called, and you're given the string, and you can do whatever you want. So in this case, this operator is splitting the string based on a regular expression. That complex-looking regular expression is just breaking the line based on punctuation and space boundaries, and giving you words. So that's standard Java function, right? And then it's just looping through the words and sending it to the next operator using the output port. So to send data out to the next operator, you define an output port and you call emit on it, right? And if you remember the 2 slides before, the output of the parser was being basically connected to the input of the next operator counter, and then the output of the line reader was being connected to the input of the parser. So in the add stream methods, we actually specified those input and output ports for connections, right? So next, if you look at the counter operator, it basically has, this one is slightly special. It has memory. For example, it has state, right? So it has a map of the counts. So it's keeping a track of how many times each word occurred. and this map is not going to go away. It's that those counts are going to remain even when there is a failure and failure recovery. So unlike the parser, which didn't have any other memory, right? So this operator, as soon as it gets a word from word, it basically is looking into the map, getting the current count, incrementing it, right? And at the end of every window, it's basically emitting the current counts, and it's not clearing the map, so that map's counts will remain and will keep growing. So here's a synopsis of our of the different types of operators that we have. We have more than 100 operators in the library, but this is just a high-level overview of the important ones. So different kinds of messaging, NoSQL, RDBMS, parsers, all kinds of different operators that are available, and all the popular ones that technologies that people use. This is how our monitoring console looks like that DataTorrent provides. So on the left side, you can see the sample application. This is our ingestion application. This is a HDFS to HDFS syncing application. There are 6 operators, and you can see that they have connections. They have more than one connections between them. That's allowed, so you can have multiple input and output ports. And the console is going to show you all the operators. It's going to show you the amount of resources each operator is using and the entire application is using, and give you all that information. On the right side, you see the same application in a different view, which we call the physical plan. Here you can see all the partitions of each operators. So the block reader and block writer are actually running as 4 different partitions. So you can see them, and they're connected in using parallel partitions. So you can see that there's no shuffle happening between block reader and block writer partitions, right? So and all these stats are continuously changing as these applications are running. So this is the screenshot of our dashboard widgets that we provide. So if you want to just visualize metrics in your application, you can use them. If you are, for example, you want to actually, your output of your application itself needs to go to a real-time widget, you can do that as well. So maybe you're looking at some outages based on geolocation, and you want to basically keep an eye on it, and if somewhere the outages increase beyond a certain threshold, you want to act on it, right? And let's say somebody is on a console looking at it, then this would be a way they can do it. So they can connect the output of the application directly to a UI widget. So we provide operators for that. And the next few slides show some of our some customers where DataTorrent and Apex are being used in production. So these are people who have talked about using DataTorrent and Apex publicly. It's being used in many other places, but these are some of the folks who have talked about it in meetups and presentations. So PubMatic is an ad analytics company for publishers. So you basically see, if you go to a website, you see ads, right? So the website is basically called the publisher, and they want to find out which ads are performing well and which are not, and which pages they are performing well, which location in the page they are performing well, and so on. So they are able to use Apex and DataTorrent to compute these in real time and make decisions as to which ads to continue to buy and which ads which are no longer performing well. Earlier, this used to happen on a scale of days, right? Now this is happening in the scale of seconds. GE has basically built an industrial IoT platform called Predix, and they are using again Apex and DataTorrent to ingest data at a very high scale. So typically their customers basically are basically industrial customers, right? These are actually, they're using machines, engines, and all these things built by GE, and all these machines have a lot of sensors and they send a lot of data. So a typical customer could be sending millions of events per second, and they want to get all the data, not lose any data while it's coming in, and process the data, perform some filtering and processing of the data before they store it. So they're using Apex and DataTorrent for that. Silver Spring Networks, they provide the network for smart meters. So they're a leader in this space. So if you many of us in our homes, we have energy meters that communicate, right, and communicate their daily usage and so on, or hourly usage of our energy to the utility, and then we can also see that utility also provides as a view for us to see how much energy we are consuming. So these guys provide all the network for that, and they also analyze and perform analytics on the data to predict what parts of your power delivery system could be failing or basically are in trouble, so that they can do preventive maintenance before those systems go down. And here's some links for the different use cases. I'll put up the slides on the meetup page in the next day or two. So so you can get these links as well. And these are some general resources for Apex and examples. And if you're a startup, you can use, you can get a free license of DataTorrent for your use. And of course, if you're using Apex, it's free. It's open source anyway. Okay. And any other questions? So there's one question: what's the difference between Apex and Hadoop plus Spark for memory processing? So we also need Hadoop, right? So it would be Hadoop plus Apex or Hadoop plus Spark. So Spark, what happens is Spark is internally a batch processing engine. Even Spark streaming is built on the same engine, so it's micro batches, which means data has to be batched before it can be processed, which introduces latency, which means the first piece of data that arrives has to wait till the last piece of data in the batch has arrived and the entire batch is formed before it can be processed. So your latency will be in the order of seconds. You can't go down to milliseconds. The other differences are with Spark, you have to handle state in different ways. So you have to do explicit handling of state in your logic. With us, you don't even worry about it, right? So you saw the counter operator, for example. It has state, but you didn't know it had state. You just had some variables where you were counting aggregates, and with us, the failure recovery is also much faster and more incremental. Okay. Any other questions? Can you compare Apex and Flink? Yeah, so Flink is also a stream processing engine. So differences with Flink, primary differences are failure recovery. So we basically can do incremental failure recovery. So let's say you have a DAG, and like I mentioned, let's say your operators 1, 2, 3, 4, and 5. 3 goes down. Only 3, 4, 5 need to be restarted from checkpoint. 1 and 2 can continue working. With Flink, I believe the entire DAG would have to be restarted. The second thing is with us, dynamic scaling is a pretty mature feature, and it's been there for us with the platform for years. I believe Flink has just introduced it, so I'm not sure how mature it is. And the third thing is our library. We provide hundreds of operators that are actually certified and ready to use, right? And these actually are production ready operators. So with Flink, you basically don't have that variety of library of operators. Okay. Yeah. So any other questions? Okay. Thank you everyone for coming to the webinar. Hope you have a good weekend.